Hi, and welcome to lesson 1 of what will ultimately be 5 lessons on complex numbers. Sort of traditional way to start something like this, the way you would see if you picked up a textbook and started taking a look at complex numbers, was just a flat out, let's introduce them right off the bat. And I'm going to do that at the second lesson, but I like to sort of provide some context. I find sometimes if you just sort of start to introduce some things and without any context to them, although the rules are all there, you sort of go, why? Why is this the way it is? Why do we have to talk about these things called complex numbers? Why would anybody even come up with this kind of stuff, and what use do they have? So I'd like to start off with just a little bit of history. Just sort of develop, where did the idea come from? What kind of problems were these people trying to solve, and why did this idea of complex numbers really mean anything? Why did they need them? Okay, so we're going to start off with a little bit of history. If you don't like the history part, go on to lesson 2. You can probably start there without ever seeing this, but well, that's the way I'm going to start. So, a little bit of history. So this is going to be introducing the complex numbers and the history component to it. And in fact, I'm never going to use the word complex numbers after this introduction. We'll talk about that in lesson number 2. What I'm going to start with is solving the cubic, which is a type of an equation that I'll get to in a little bit. And then how did learning how to work with the square root of -1, which at first glance doesn't look like it has much meaning to it at all. After all, you've probably been told in the past you can't take the square root of a negative number. But nevertheless, how does this value end up helping us get a problem when we're trying to solve a cubic equation? So a little bit of history. Let's get into this. So first of all, solving equations. And solving equations is an important part of mathematics. And the degree of the equation is just the exponent that would be on the variable. So like, this is just an x to the 1. So this would be an equation of a degree 1, or what's often called a linear equation, and a equation in standard form. And to solve this, well, it's simple enough. You simply take the constant, the b, and you subtract it over to the other side. You divide by the a, provided, of course, the a is not 0. I should sort of put that stipulation in there that the a can equal a 0. Just gonna throw that in there because obviously if the a were 0, then that would be 0, and that's no good. But we'll kind of understand that is a restriction on this. And besides, if the a were 0, then this term here wouldn't be here, and you wouldn't really have much of an equation at all. So there you go. Let's get rid of that. Okay, but that's an easiest one to solve. We step up the degree. We get to a degree 2 equation, or what's often called a quadratic, where there's now a square on the x. And there's a number of techniques to solving quadratic equations that you typically would learn in high school, but they all can be summarized actually with this particular solution, which is the familiar quadratic equation. Again, I'm assuming that a not equal to 0. And both of these solutions have been known for quite some time. In fact, they go back at least 4,000 years, because the quadratic formula falls straight out of the technique of completing the square, and the Babylonians 4,000 years ago knew how to complete the square, so they knew how to solve a quadratic equation like the one we have here of degree 2. So that's simple enough. What about if we step up to degree 3? Degree 3, we get something called a cubic with an x cubed term in it, but this one proved to be much more problematic, and solving the cubic equation became an important and elusive pursuit of mathematicians for millennia. A common technique when trying to solve a complex problem is to start with a more simple version of the problem. So that's why studying what are called depressed versions of the cubic, like this one, became an important idea. And notice in this one we've lost the squared term. There's no more, so it's still a cubic, but it's a simpler version of the cubic. The also thing we did is that the coefficient here is just going to be a 1. Again, simpler still. So we have ourselves a simpler version of the cubic. And it was a mathematician who worked at the University of Bologna by the name of Scipione da Ferro, who lived in the 15th century, who came up with this particular solution. Now, don't worry so much about memorizing the solution. The first to look at is like, oh my God, I can see why this was taking so long. Don't memorize it. It's no big deal. Okay? But this does give a solution to an equation of the form x cubed plus ax is equal to b. Okay? And although the derivation of this formula is beyond the scope of this particular lesson, we can see the formula at work. So why don't we do that? Why don't we use this formula to solve x cubed plus 6x is equal to 20. So that's simple enough. The value for a, which is the coefficient in front of the x, would be a 6. The value for b would be a 20. Okay. Substituting into the formula, this is our formula again, so we just substitute in our values for a and b, and we get this. We do a little bit of calculating, not too bad. We can reduce all those fractions and doing a little bit of adding down to this. And today what we would do, actually, I'm going to show you a technique which is a bit of an optional thing, but I'd be perfectly good at this stage with just putting this into our calculator, and you would find out that the answer is 2. And it's pretty easy to verify that 2 is indeed the solution by just going up to the equation and seeing if we put 2 in for the x, does it come out to be what it's supposed to, which is 20. Well, let's see, like if I take 2 and I cube it, and I add that to 6 times 2, well, 2 cubed is equal to 8. Whoops. There we go. And 6 times 2 is 12. And then 8 plus 12 is indeed 20. And that's what it's supposed to be. So x equals 2 is a solution. This equation does seem to be working. Okay. Now you might be asking yourself, okay, well, using a calculator, isn't that, it might feel like a bit of a cheat, because certainly Del Ferro in the 15th century wouldn't have had access to an electronic calculator. So I'm going to show you what he might have done, a technique that actually will reduce this particular expression without the use of a calculator. And the reason why I'm going to show this is because it's going to come up again in just a little bit. Now this is a bit of an aside, and if I lose you a little bit, don't worry about it. It's kind of optional. Okay? But let's go through this and see if we can do this without a calculator. Well, there's our expression we got to. That was easy enough to get down to that. We can do a little bit of manipulating. And what I did is I took this negative sign right here and I took it out of the cube root. You're allowed to take negatives outside of odd numbered roots like cube roots without a problem. That would change the operation between the two cube roots to be addition. Of course, that would also change that sign to its opposite, so it's now a negative as well. So that's what happened there. The other thing that I can do is I can reduce the two radicals. Okay, I have the square root of 108 in there, and that can be simplified because the square root of 108, if I can find perfect squares that will divide into what's inside the square root, I can reduce it. And I want to find the biggest one that I can, and a little bit of digging wouldn't take you too long to figure out that 36 divides into 108. And in fact, 108 is 36 times 3. So I can reduce the square root of 108 to the square root of 36 times the square root of 3. I can take the square root of 36 without a problem. It's a perfect square. It's square root of 6. Square root of 3 would be irrational, so I'm not going to do anything with that. So I get 6 root 3. So that's what I did here. Change the square root of 108 to a 6 root 3. Same thing here, except of course now it's a minus 6 root 3. Easy enough. Okay. Here comes the clever bit. And at first this doesn't seem to have any connection. Now Del Ferro would have known how to cube a binomial. And hopefully you've seen this formula before, that if I take a binomial like a plus b and I cube it, I get a cubed plus 3a squared b plus 3ab squared plus a b cubed. And this expression comes straight out of what today we would call the binomial theorem. Okay. But what we can do is we can use this to help us figure out what these cube roots are. Now you need to do a little bit of playing around. But a little bit of playing around would have gotten you that 1 plus the cube root of 3 cubed. And at first it seems like where the heck does this come from, this 1 plus the cube root of 3? But I'll talk about that in a little bit. It's not 100% random. But if I cube it, I get this expression here, 1 plus 3 root 3 plus 3 root 3 squared plus root 3 cubed. And all I'm doing is putting 1 in for the a in this expression and the square root of 3 in for the b. That's all I've done, is replaced the a and the b with those two. And you can go through and you can do that. There's a little bit of simplifying that can be done here, because if I take a square root and I square it, square rooting and squares are opposite operations, so they will undo each other, and I'll be left with just the argument inside the square root. So the square root of 3 squared would just be 3. I'll write that off to the side. Square root of 3 squared would just be 3. So that simplifies down nicely. What about the cube root of 3? Well, the cube root of 3, or sorry, not the cube root, the square root of 3 cubed, how can I deal with that? Well, the square root of 3 cubed can be written as the square root of 3 squared times another square root 3. That's the same as the square root of 3 cubed. And we just decided that the square root of 3 squared would be a 3. So if I square the square root of 3, that would be 3 times this other square root 3. So the square root of 3 cubed can be reduced to 3 root 3. And that's what I did in the next line. Okay, let's get rid of all this other stuff that I wrote. So the square root of 3 squared right here would be 3 times this 3 would get me the 9. And the square root of 3 cubed would be this 3 root 3. And the thing to notice is I got some like terms that I can combine together. I have a 3 root 3 and another 3 root 3. I can add those together to get 6 root 3. I also have the more easier 1 plus 9, which of course is 10. So combining those two like terms together, I get 10 plus 6 root 3. Okay, so what? Well, the thing to notice is that this 10 plus 6 root 3 is exactly the same as what's inside this first cubed root. So I have something being cubed coming out to be this. Well, that means that the cube root of 10 plus 6 root 3 must be 1 plus the square root of 3. Okay. So we were able to work out that cube root. So de Ferro was able to deduce that the cube root of 10 plus 6 root 3 must be 1 plus root 3. Similarly, you can do a similar argument. You can do the work if you like to, but you would get that the cube root of 10 minus 6 root 3 would be 1 minus the square root of 3. So that allows us to do some simplifying. So now I can take these two cube roots, I can replace them with their respective results. And notice what kind of happens here. I have a root 3 and a minus root 3. Well, root 3 minus root 3, that's going to be 0. And then I have the 1 plus the 1. That's just going to be 2. So this works out kind of nice. The root 3's are gone. 1 plus 1 is 2. My answer is 2, which we already worked out was indeed the solution. All right. Again, this was an aside. Don't worry if I kind of lost you in there a little bit. So far, though, this has all been, although there's been some messy root work, nothing too strange going on there. What does this have to do with the square root of -1? Well, a little bit later on, a guy by the name of Guillermo Cardano, who's often just known as Cardan, who worked in the early part of the 16th century, was also studying the cubic, and he was studying cubics of this form. And he came up with this solution, remarkably similar to de Ferro's solution. And I want to draw a little bit of attention to the similarity between the two. De Ferro's equation that he had his solution for was this. This was de Ferro's. It was x cubed plus ax plus a b, or equals b. Okay. And here we have Cardan's, which is x cubed plus equals ax plus a b. And you might be wondering, wait a second, isn't this really just the same equation, just with the ax term moved over to the right side of the equation, which would just change its sign to an opposite? So for instance, if I had went back to my previous equation that we just solved, we had x cubed is equal to, sorry, that's not what we had. We had x cubed plus 6x. That's supposed to be a plus now. Plus 6x. Let's see, I should have an eraser here. There we go. Sorry about that. That's a little better. That's a plus 6x. This was the one we just had. X cubed plus 6x is equal to 20. Can't I just take that 6x term, take it to the other side, and write that? And then that would be now an equation in Cardan's form. And in fact, you would probably be wondering, why even bother having Cardan's form of this equation? You could just rearrange things and stuff them into the formula we just had. Well, there's a reason why they wouldn't have done that back then in the 15th and the 16th century. And the reason seems pretty strange today. The reason is because they didn't consider negative numbers to be actual numbers. Okay. They would never have written x cubed equals negative 6x plus 20 because of that negative 6x. They would go, well, that doesn't make any sense. Today, that seems really, really strange to do that. But back then, for every particular number, they needed to have sort of a physical meaning towards that number. Could you hold negative 6 apples in your hand? Could you cut a piece of stone to be negative 6 units long? No, of course not. That doesn't make any sense. And because they couldn't wrap their head around a physical interpretation of a number like negative 6, they would have considered that number nonsensical. They would consider this second equation to be a nonsensical equation with the negative 6x term in there. If they were working with a problem and they ended up with results that would be negative, they would have just simply discarded those results as having no meaning whatsoever. So they didn't consider negative numbers as being actual numbers. Excuse me. And that seems really strange to a modern high school student who's been working with negative numbers for a long, long time and been solving real-world problems with negative numbers. So why am I belaboring this? Why am I going on about this whole thing about 15th and 16th century mathematicians not believing in negative numbers? Well, the reason is because very soon we're going to work with a number that at first glance also doesn't seem to have any meaning. And you are, if you're like most people, pretty much guaranteed to have kind of a negative, if you excuse a little bit of the pun there, a negative reaction to it. You're going to look at the number and you're going, this can't mean anything. This number makes no sense. And I want to point out in advance that you are reacting in exactly the same way as a 15th and 16th century mathematician would have reacted to negative numbers. Okay. But you know now that negative numbers do have meaning. They do have uses in solving real-world problems. And this new type of number that's coming up, well, you'll also see, will have uses at all. So I do want to point out that his contemporaries would not have considered a negative number to be a real number. I'm using real numbers in quotation marks because I don't mean. No. Okay. So that's why Cardan's version of this solution is considered to be a distinct from Del Ferro's. Anyways, let's use Cardan's formula to solve this particular equation. So this one here, x cubed is equal to 15x plus 4. Okay. Seems simple enough. So the a would be a 15, the b would be a 4. Here's Cardan's formula. We substitute in. Whoops. There we go. We substitute in. We do a little bit of simplifying. We get down to this. Now, most mathematicians of Cardan's time would have taken one look at this guy and said, that's it, we're done. That makes no sense. And in fact, perhaps you're even saying that. I got the square root of negative 121. How can I take the square root of a negative number? You've probably been told in the past you can't take the square root of a negative number, in which case you would probably say at this point, this question can't be done. We're done. No solution. We're done. Here's the issue, though. Cardan and his student, he had a student that was working with him on these as well, named Raphael Bombelli. And they already knew that x equals 4 is a solution to this particular equation. In fact, it's pretty easy to see that x equals 4 is a solution. We just have to go back up here and see that it works out. If I take 4 and I cube it, I'm going to get 64. And if I look over at the right side of this and I take 15, and I multiply it by 4 and add 4 to it, well, 15 times 4 is 60, and then 60 plus 4 is 64. So 4 is a solution, despite the fact that we got this square root of a negative. And what Cardan and Bombelli reasoned was, and they happened to reason correctly, perhaps this somehow simplifies down to 4. Somehow we can work with this. So what they did is they didn't try and wrap their head around what could possibly be meant by the square root of negative 121. They just sort of persevered and kind of worked with the math that they knew and see if they can get this down to something that does make sense. Okay. First thing to do is they took a closer look at the square root of a negative 121. And they noticed that 121 is a perfect square. Square root is 11. So what they did is they split it up. Square root of negative 121 can be written as the square root of 121 times the square root of negative 1. And you can take the square root of 121 and you can get 11. So you get 11 times the square root of negative 1. So that allows them to take the expression that they've gotten so far and to sort of simplify it a little bit. Doesn't get the answer yet, but it makes things look a little bit nicer. I did two things here at the same time. I should point them out. Number one is I took this negative sign here, just like I did before, and I took it out of the cube root, which would make that a positive. And of course, that forces me to change this sign to its opposite, so it's now a negative here. So we took that negative out of that second cube root, made it an addition of two cube roots. And then the more obvious thing I did is I took the square root of negative 121 and replaced it with 11 times the square root of negative 1. Okay, so that's what's going on there. Okay, they still got some work to do, and they got the square root of negative 1, which again, they really couldn't wrap their head around what that could possibly mean, but they did figure a few things out. Number one they figured out was, well, if I took the square root of negative 1 and I squared it, square roots and squares are still opposite operations, so if I square a square root, I should just get the argument that's inside the square root. So in this case, I should get a negative 1. So the square root of negative 1 squared should be negative 1. Seems reasonable. Okay. They also thought about, what about the square root of negative 1 cubed? Can I work with that? Well, sure you can, because square root of negative 1 cubed must be the same thing as the square root of negative 1 squared times another square root negative 1. And we already reasoned that the square root of negative 1 squared would just be negative 1. So this would be negative 1 times the square root of negative 1, which would get us negative square root negative 1. Okay, so although they don't quite get square root negative 1, they did figure some things out. They figured some work that they can do with it. And then they went and they noticed this, that if I take 2 plus the square root of negative 1 and cube it, using that same pattern for cubing a binomial that we had before, we get this. Okay. And we can do some working out. This isn't so hard to work out. There's some pretty, 2 cubed here would be an 8. We have 3 times 2 squared. 2 squared is 4 times 3. That would get us a 12. We have this negative 1 squared, which we can replace with a negative, with a negative 1. And we have this negative 1 cubed that we can replace with a negative. This negative 1 cubed here, which we can replace with a negative square root negative 1. So let's do all that. We end up with this. Okay. And then we got some like terms that we can collect together. We have a 12 square root negative 1. We have a minus square root negative 1. Well, that's going to get us 11 square root negative 1. And then we have the more familiar 8 minus 6, which of course is 2. So we get down to this. And again, the thing to notice is that that is the same as that. Okay, so if I take 2 plus the square root of negative 1 and cube it, I get the same thing that's inside this cube root. That means that the cube root of 2 plus 11 times the square root of negative 1 must be 2 plus the square root of negative 1. I want to point out at this stage that we're not just picking this at random. It seems like it comes out of nowhere. But there's a little bit of reasoning that can go into deducing what would be a good candidate to cube to get this. One, it does help to know the answer. Remember, the answer was that x is equal to 4. And taking a look at these two parts here, it would be really nice. Notice that they're almost the same except one's got a negative and one's got a plus. It would be really nice if part of this worked out to be a 2 plus another 2, because that would get us the 4, which is what we know we want. The other thing that would be nice is we got the square root of negative 1s. It would be nice if they kind of just went away. if one came out to be a positive, one came out to be a negative, and they would end up subtracting off each other. Similar to what happened with Del Ferro's formula, if you look back a few slides, where the two roots canceled each other out. So it would seem reasonable that 2 should be part of what we're cubing. And it also seems reasonable, because we want these square roots of -1s, that the -1 should be part of what we're cubing. Okay. Don't worry so much if you don't really follow that logic. It doesn't really matter. But I do want to point out that it's not like they're just working and they're stabbing in the dark. There is some reasoning, some backwards engineering that you can do to kind of work out what would be a good candidate to cube and get 2 plus 11 square root -1. Anyway, onwards. So they deduced that the cube root of 2 plus 11 square root -1 must be 2 plus the square root of -1. You can use very similar piece of logic and show that the cube root of 2 minus 11 square root -1 must be 2 minus the square root of -1. So we can take our expression that we've gotten so far. We can now replace the two cube roots with 2 plus the square root of -1, and then plus 2 minus the square root of -1, and we get exactly what we want to happen. The 2 square root -1s, although we never did wrap our head around kind of what the heck does that mean, it turns out it doesn't matter in this problem, because the square root of -1 minus another square root of -1, we can reason must be 0. And then we're left with 2 plus 2, and of course 2 plus 2 is just 4, which we already knew is the correct answer. Okay. So what to glean from all of this? Number one is the square root of -1. Just because we can't, at this stage, wrap our head around a physical interpretation of what exactly that means, that doesn't mean that it doesn't have any use. In this case, it came up as an intermediate step and eventually got us to our correct solution. So that's one of the things that Cardan noticed right away is, well, number one, his answer is correct. And number two, the mathematics that he used is perfectly sound. So although they didn't wrap their heads around the meaning of the square root of -1, they couldn't help but notice that it still gave them a real world and correct answer. And that's something we're going to see as we progress through the rest of these lessons, is that happening all the time. Just because the square root of -1 isn't something that you can necessarily count out or measure, that doesn't mean that it doesn't have a use. And that doesn't mean it doesn't have an application to real world problems. And we're going to see a number of real world problems that are going to come up that's going to have our use. Okay, that ends sort of the history component of this. In part two, we're going to define things a little bit more precisely, a little bit more, use some little bit more modern notations, and start taking a look a little bit more closely at what kind of numbers are we getting when we start taking the square roots of negative numbers. Until then, you can work on some problems of your own. Accompanying these sets of lessons, you will find a set of notes, and what I think would really help is to actually follow through the video with the set of notes, and then at the end of each section of the set of notes you will find a set of problems. And so if you want to try and work on these a little bit yourself, I personally think that there's only so much math that you can learn by watching other people do math, and in the end you have to pick up a pencil and a paper and you got to do it on your own. So here are some problems for you to try. At the back of the notes you will find full solutions if you get yourself stuck. But try and see if you can do these without cheating and taking a look at the solution. All right, till the next video, we'll see you then.